Assalamu alaikum and welcome back to our series Science and the Quran, the story of sunshine and iron. We had left off considering this amazing verse of the Quran. أعوذ بالله من الشيطان الرجيم أفرأيتم النار التي تورون أأنتم أنشأتم شجرتها أم نحن المنشئون. Have you ever considered the fire which you kindle? And when the Quran asks a question like that, I think for those of us interested in science, we should consider it in a deeper way than saying, wow, that's amazing. أأنتم أنشأتم شجرتها أم نحن المنشئون. Is it you that have brought into being the tree that serves as its fuel, or are we the cause of its coming into being? And we said the fact that wood burns is actually the result of a very amazing set of circumstances. It is a set of organization such that their stored chemical potential energy, the reactants, which are wood and oxygen, have a higher level of stored chemical energy than the products, which are carbon dioxide and water vapor and ash. And so this reaction is favored by nature. Nature likes reactions that flow down the energy hill and release energy. If it was the other way around, we would have to keep putting energy into the system. However, we said that the Quran here makes a very subtle point. النار التي تورون, the fire that you kindle, and that this reaction doesn't actually proceed entirely spontaneously. For example, when you add baking soda and vinegar for making those science fair volcanoes, that reaction proceeds spontaneously. If you were to add glycerol and permanganate, that reaction bursts into flame spontaneously. But the burning of wood is a different sort of reaction, where the reactants are indeed at a higher energy level than the products. So the reaction likes to proceed and likes to release energy, but it requires some activation up front. And that activation energy is, for example, you lighting a match to kindle the fire. And that is really a remarkable set of circumstances, because we want wood to burn, we want coal to burn, we want oil to burn, we want natural gas to burn, because you are aware of how much civilization depends on those things, but we don't want that to happen spontaneously. We don't want the wood in our houses and in our forests to combust spontaneously. So we want precisely this level of chemical organization. And I think that this is the way we should consider this verse, that it is really an amazingly balanced system. But remember, this was all a sidetrack to highlight the difference between combustion, such as the burning of coal, and what is happening in the sun. Ordinary combustion is a rearrangement of atoms, but the atoms themselves are not changed or destroyed. E equals mc squared does not play any fundamental role in that. However, radioactivity is an entirely different thing. It is a spontaneous change in the nucleus of an atom, where the atom itself is changed, and where there is a mass difference between the reactants and the products, and it is that mass being converted to energy by E equals mc squared that accounts for the energy of radioactivity. So back to the sun. It seemed that maybe radioactivity was the answer. Radioactivity is ideal because it gives off a great deal of steady energy in a controlled way, and the energy can be very long-lasting. We mentioned that the half-life of uranium-238 is 4.5 billion years. Now, this is the sort of number that geologists could be happy with regarding, say, the age of the Earth or the age of the Sun. But of course, there was a problem. As of 1911, radioactivity was only known in very complicated heavy atoms like uranium. However, we had said that the work of many scientists had finally unraveled that the sun is almost all hydrogen and a bit of helium. And those don't have any radioactivity. And so once again, a promising lead seems to have died out. So back now comes Rutherford. What if it's not ordinary radioactivity? In 1919, Rutherford discovers a different sort of nuclear reaction than nuclei just splitting apart, And he does this by bombarding nitrogen gas with subatomic particles and getting oxygen. So here was a genuine change in a nucleus of hydrogen to turn it into oxygen. Once again, chemical reactions like wood burning do not change atomic nuclei. The atoms stay the same but are just rearranged into different compounds. This, however, is completely different. So another form of radioactivity was discovered, not fission, and fission means the splitting apart of a heavy nucleus into two lighter nuclei, like uranium going to thorium, but fusion. So in 1915, a scientist named William Draper Harkins suggested that 4 hydrogen nuclei might be pushed together so hard that they would fuse to form helium, and that the resulting reaction, or that this reaction would release energy because there would be a difference in mass, and by E equals mc squared, energy would be released, and this is called nuclear fusion. Within a few years, scientists had learned enough to know that this reaction, if it could happen, would produce more energy than any other reaction known to man. This would be enough to power the sun and to last for billions of years. But, once again, problem. The temperature of the sun, about 10,000 degrees Fahrenheit, doesn't supply the necessary energy to produce the fusion reaction. It doesn't supply the necessary energy to push the hydrogens together fast enough and hard enough to make them fuse. So once again, after accurate measurements of the surface temperature of the sun were obtained by spectra and so forth, it seemed that yet another promising lead may have it died out. So now, a side calculation. Remember Arthur Eddington when we talked about relativity. He was an astronomer interested in general relativity, and I have a note here on the slide, anecdote here. And I may have mentioned this anecdote before, but if I don't remember telling it, you probably don't remember hearing it. He was the fellow that once Einstein published his theory of general relativity, it was so complex that the British press went to Arthur Eddington and said, "Professor Eddington, is it true that this theory is so complex that there are only 3 people in the world who understand it?" They went to him because they knew of his interest in general relativity, and he replied and he said, "Oh really? Who is the third?" So that just a little side joke there to amuse you along the way. But Eddington's question was, why doesn't the sun collapse under its own gravitational pull? The old Helmholtz idea taken to the extreme. And his answer was that it must be extremely hot inside, with the core temperatures heating the hydrogen enough to expand it against the enormous pull of gravity. So how hot, you ask? Well, Eddington's calculations that what was needed to keep the sun from collapsing under its own weight was, again, and that collapse would have been governed by the equations of general relativity, that it needed to be about 25 million degrees inside the core of the sun. Remember, it's about 10,000 degrees at the surface, but it's 25 million degrees in the core. And these calculations were done in the 1920s. Now, at these temperatures, hydrogen fusion does become possible. So by 1938, enough was known about atomic physics to finally start to calculate what was going on inside the sun. The hydrogen had to fuse to helium, and Eddington's calculations showed that the sun's core temperature was hot enough to do that, but that's not the end of it. It had to fuse slowly enough not to explode, but quickly enough for the sun to radiate as much energy as it does. So, given what we have learned about the physics of fusion so far, scientists were asking, is this what happens? And Hans Bethe did the calculations and found that the fusion proceeds just as needed given the conditions deep in the sun as calculated by Eddington. Another scientist, Carl Friedrich von Weizsäcker, he independently did the calculations and got the same results, and all of a sudden scientists were now very hopeful that this was the answer. The sun was indeed powered by radioactivity, but it was the radioactivity of hydrogen fusing into helium, and that could give the spontaneous energy that the sun seemed to emit. And again, I have another note here about an anecdote about alpha and gamma. They were two famous particle physicists who wrote a paper on nucleosynthesis in the Big Bang, and they invited their friend Hans Bethe, even though he didn't really work on the paper, to join them so that the list of authors on the paper would be alpha, beta, gamma. And of course, that sounds remarkably like the first three letters of the Greek alphabet, alpha, beta, gamma, and they thought that that was very funny, that that would be the list of authors. And I end this lecture with that anecdote just to show you how impish and funny physicists are, lest you think science is boring. We will pick it up from here, inshallah, in the next lecture to look at a little bit more detail, and finally to look at the Quranic verses that I know you have been waiting for and wondering, hey, this is all science, where's the Quran? Inshallah, we will get into now the Quran with the background of the science that we've developed. Assalamu alaikum, and see you soon, inshallah.